came out of it like really early, 2018. So this is 4 years before flash attention. And this paper says that we propose a way to compute the classical softmax with fewer memory accesses and hypothesize that this reduction in memory accesses should improve softmax performance on actual hardware. And so they are extremely correct in this hypothesis. But it's really fascinating to me that they're from NVIDIA and that they had this realization, but they didn't actually take it to the actual flash attention. That had to come 4 years later from Stanford. So I don't fully understand the historical, how this happened historically. But they do basically propose this online update to the softmax right here. And this is fundamentally what they reuse here to calculate the softmax in a streaming manner. And then they realize that they can actually fuse all the other operations with the online softmax calculation into a single fused kernel, flash attention, and that's what we are about to use. So a great example, I think, of being aware of memory hierarchy, the fact that flops don't matter, the entire memory access pattern matters, and that torch compile is amazing, but there are many optimizations that are still available to us that potentially torch compile cannot find. Maybe one day it could, but right now it seems like a lot to ask. So here's what we're going to do. We're going to use flash attention, and the way to do that, basically in PyTorch, is we are going to comment out these 4 lines. And okay, so as we can see, we are currently at about 300 million. Now, torch compile is, and this has never materialized. And the way that this is achieved is that basically the fundamental algorithmic rewrite here relies on this online softmax trick, which was proposed previously, and I'll show you the paper in a bit. And the online softmax trick, coming from a previous paper, shows how you can incrementally evaluate a softmax without having to sort of realize all of the inputs to the softmax to do the normalization. And you do that by having these intermediate variables M and L, and there's an update to them that allows you to evaluate the softmax in an online manner. Now, flash attention, actually, so recently flash attention 2 came out as well, so I have that paper up here as well, that has additional gains to how it calculates flash attention. And the original paper that this is based on, basically, is this online normalizer calculation for softmax. And remarkably, it came out of NVIDIA, and it came out of it like really early, 2018. So this is 4 years before flash attention. And this paper says that we propose a way to compute the classical softmax with fewer memory accesses and hypothesize that this reduction in memory accesses should improve softmax performance on actual hardware. And so they are extremely correct in this hypothesis. But it's really fascinating to me that they're from NVIDIA and that they had this realization, but they didn't actually take it to the actual flash attention. That had to come 4 years later from Stanford. So I don't fully understand the historical, how this happened historically. But they do basically propose this online update to the softmax right here. And this is fundamentally what they reuse here to calculate the softmax in a streaming manner. And then they realize that they can actually fuse all the other operations with the online softmax calculation into a single fused kernel, flash attention, and that's what we are about to use. So a great example, I think, of being aware of memory hierarchy, the fact that flops don't matter, the entire memory access pattern matters, and that torch compile is amazing, but there are many optimizations that are still available to us that potentially torch compile cannot find. Maybe one day it could, but right now it seems like a lot to ask. So here's what we're going to do. We're going to use flash attention, and the way to do that, basically in PyTorch, is we are going to comment out these 4 lines, and we're going to replace them with a single line. And here we are calling this compound operation in PyTorch called scaled.product attention. And PyTorch will call flash attention when you use it in this way. I'm not actually 100% sure why torch compile doesn't realize that these 4 lines should just call flash attention in this exact way. We have to do it again for it, which in my opinion is a little bit odd, but here we are. So you have to use this compound up, and let's wait for few moments before torch compile gets around to it. And then let's remember that we achieved 6.05661. I have it here. That's the loss we were expecting to see. And we took 130 milliseconds before this change. So we're expecting to see the exact same result by iteration 49, but we expect to see faster runtime because flash attention is just an algorithmic rewrite and it's a faster kernel, but it doesn't actually change any of the computation and we should have the exact same optimization. So, okay, so we're a lot faster. We're at about 95 milliseconds and we achieve 6.058. Okay, so they're basically identical up to a floating point fudge factor. So it's the identical computation, but it's significantly faster, going from 130 to roughly 96. And so this is 96 divide 130-ish. So this is maybe 27-ish % improvement. Really interesting, and that is flash attention. Okay, we are now getting to one of my favorite optimizations, and it is simultaneously the dumbest and the most brilliant optimization, and it's always a little bit surprising to me. Anyway, so basically I mentioned a few minutes ago that there are some numbers that are nice and some numbers that are ugly. So 64 is a beautiful, nice number. 128 is even nicer. 256 is beautiful. What makes these numbers beautiful is that there are many powers of 2 inside them. You can divide by 2 many times. And examples of ugly numbers are like 13 and 17 and something like that. Prime numbers, numbers that are not even, and so on. And so pretty much you always want to use nice numbers in all of your code that deals with neural networks or CUDA, because everything in CUDA works in sort of like powers of 2, and lots of kernels are written in terms of powers of 2, and there are lots of blocks of sizes 16 and 64 and so on. So everything is written in those terms, and you always have special case handling for all kinds of logic that when your inputs are not made of nice numbers. So let's see what that looks like. Basically, scan your code and look for ugly numbers is roughly the heuristic. So 3 times is kind of ugly. I'm not 100% sure. Maybe this can be improved, but this is ugly and not ideal. 4 times is nice, so that's nice. 1024 is very nice. That's a power of 2. 12 is a little bit suspicious. Not too many powers of 2. 768 is great. 50,000 to 57 is a really, really ugly number. It's, first of all, it's odd. So and there's not too many powers of 2 in there. So this is a very ugly number, and it's highly suspicious. And then when we scroll down, all these numbers are nice. And then here we have mostly nice numbers except for 25. So in this configuration of GPT-2 XL, the number of heads is 25. That's a really ugly number. That's an odd number. And actually, this did cause a lot of headaches for us recently when we were trying to optimize some kernels to run this fast and required a bunch of special case handling. So basically, these numbers are, we have some ugly numbers, and some of them are easier to fix than others. And in particular, the vocab size being 50,000 to 57, that's a very ugly number, very suspicious, and we're going to fix it. Now, when you fix these things, one of the easy ways to do that is you basically increase the number until it's the nearest power of 2 that you like. So here's a much nicer number. It's 50,304. And why is that? Because 50,304 can be divided by 8, or by 16, or by 32, 64. It can even be divided by 128, I think. Yeah. So it's a very nice number. So what we're going to do here is, this is the GPT config, and you see that we initialize vocab size to 50,257. Let's override just that element to be 50,304. Okay. So everything else stays the same. We're just increasing our vocabulary size. So we're adding, it's almost like we're adding fake tokens. So that vocab size has powers of 2 inside it. Now, actually what I'm doing here, by the way, is I'm increasing the amount of computation that our network will be doing. If you just count the flops on like do the math of how many flops we're doing, we're going to be doing more flops, and we still have to think through whether this doesn't break anything. But if I just run this, let's see what we get. Currently, this ran in maybe 96.5 milliseconds per step. I'm just kind of like eyeballing it. And let's see what kind of a result we're going to get. While this is compiling, let's think through whether our code actually works okay when we increase the vocab size like this. Let's look at where vocab size is actually used. So we swing up to the init, and we see that it's used inside the embedding table, of course, so all the way at the bottom of the transformer, and it's used at the classifier layer, all the way at the top of the transformer, so in two places. And let's take a look, and we're running at 93. So 93 milliseconds instead of 96.5, so we are seeing a roughly 4% improvement here by doing more calculations. And the reason for this is we've made an ugly number into a nice number. I'm going to come into the explanation for that a little bit again, but for now, let's just convince ourselves that we're not breaking anything when we do this.